Hello, and welcome to the Cole Kleinen's Philosophy Hour. Today, as usual, I'm going to be talking about something I barely understand, but whereas normally I think with a few days or weeks of reading I could normally grasp the topic in question, with this one I think it would take a lifetime to fully understand all the implications of the problem that we're going to be covering today. But the motto of the Cole Kleinen's Philosophy Hour is that it doesn't matter if you're spreading misinformation if no one who watches your video knows what you're talking about. So with that said, let's begin. Today, we're going to be talking about set theory, specifically the axiom of choice. But before we can talk about the axiom, we need to get a basic understanding of infinity within the context of set theory. But before we can talk about infinity, we need to talk about the two kinds of numbers, ordinals and cardinals. And before we can talk about ordinals and cardinals, we need to talk about the natural numbers. And before we can talk about the natural numbers, we need to talk about the idea of well-ordered sets. All right then, so first of all, what is a set? A set, denoted by curly braces like that, is just a collection of mathematical objects. So you could put anything in there, like you could have like people like this, like that, or you could like take these guys out and put like some numbers or some letters or that sort of thing. Okay, then what is an order? An order. So basically, an order is just a way to rank a set of objects. It's an arbitrary ranking of the elements in a set. So we can say, for example, A is before B, B is before C, that sort of thing. This order can be based on anything. So if we have like 3 smiley faces, this guy's like kind of meh, this guy's a little angry. We have these guys who are making up our set. We can order them based on like diameter, for instance, or how happy they are, or if they have like a little twinkle in their eye, how big their twinkle is, that sort of thing. And using those 3 different ranking systems, we can get 3 completely different but equally valid orderings. More generally, an ordering depends on the binary operator less than or equal to on some set X. That's an X. Where we can define things, we can define the meaning of less than or equal to and X based on the context. So if we have 3 unknowns, A, B, and C in our set X, then we can use these things to order them. 1. A is less than or equal to A. This is called the reflexive property. 2. If A is less than or equal to B and B is less than or equal to C, then we have A is less than or equal to C. And this is called the transitive property. Oh, get this stupid string. Shit. Get out of here. You're getting in my way. Okay. Well, that's sort of out of the way. Number 3. If A is less than or equal to B and B is less than or equal to A, then A equals B. And this is called asymmetry, the asymmetric property. And then finally, number 4, if it holds, or no, not if, but A must be less than or equal to B, or B must be less than or equal to A. One of these must be true, or else it doesn't make any sense. And this is strongly connected. Boom. So using these fundamental principles, which I think are more or less evident, we can order any set. Now this brings us to the definition of a well-ordered set, which is an ordered set that has a least element. This is equivalent to saying every non-empty set S of non-negative integers contains a least element. Or in symbols, we can write there exists A in a set S such that, let's see here, A is less than or equal to B for all B in S. I hope that was in frame. But you're going to be seeing some of these sorts of symbols. If you're not familiar with them, this means like is an element of, so A is an element of S. This means there exists, so there exists A in S. Two dots is usually like such that. The upside down A sign like this is for all, so B, A is less than B for all B in S. You know, it's not too complicated once you get the hang of it. But now we've arrived at the quintessential well-ordered set, which is the natural numbers, denoted by, like this, a double struck N. That's what that's called. Where N equals this set. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, dot, 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 and so on to infinity. And depending on who you ask, 0 may or may not be part of the set. And we will talk a little bit about that in a moment. But for now, I'm going to be using the ISO 80000-2 standard, a very, very important standard. And I will include, oh wait, I didn't include 0. 0. I will include 0 in the set of natural numbers. That should have been there. Fuck.
Ah, pues entonces no se queje y agarra un pinche grupazo. Que le cobre $6,000 todo. Y aparte otros 6,000 ya valió.
Oh, to be a mallard in a stream. Oh, he's taking a drink. Slurp. Thirsty. Natural numbers are useful in many ways. They can be used for counting, as in, I drank 8 beers before going on a relaxing drive, in which they serve as cardinal numbers. Or they can be used for ordering, as in, I am the first element in the well-ordered set of handsome boys recording an episode of the Cole Kleinen's Philosophy Hour about the axiom of choice in a semi-urbanized area on a university campus, in which they serve as ordinal numbers. Natural numbers are also sometimes used as labels. For example, as in like sports jerseys, if I'm the number 15, then that's called a nominal number, because I am a number, and that is my name, and my name is 15. In which case they do not have the properties of numbers in a mathematical sense. Sandesh, what do
Yeah.
you think about the axiom of choice?
Oh, that's an interesting question. I think it's the first person who stepped on Mars,
Yeah?
isn't it? Yeah, it is.
Yeah.
And oh, isn't his nickname Skibbity?
Yeah.
Oh yeah, that's That's correct. That's what is axiom of choice, bro.
Yeah, type
Type
shit.
shit.
Type shit.
Type shit, bro.
Okay. Now we are really starting to make some real progress, and we have come to the next topic on the road to the axiom of choice. We have cardinal numbers and ordinal numbers. Two different kinds of cool ass numbers. So, as I just mentioned, cardinal numbers are counting numbers used to count the total number of elements in a set. Ordinal numbers are ordering numbers used to enumerate the position of each element in the set. So if we have a set of 5 smiley faces, like this, 1, 2, 3, 4, 5, and this guy is like super happy, this guy's pretty happy, this guy's all right, this guy's a little unhappy, a little bit. This guy's really unhappy. He's so angry because he doesn't know what the axiom of choice is. So we would say that the cardinality of this set, which is, if this set is S for smiley face, we'd say like that. That means cardinality is 5 because there's 1, 2, 3, 4, 5 elements in the set. If the set is well ordered based on the happiness of each smiley face, I could point to, for example, this guy right here, the third element in the set, and say that he has ordinal number 3 because he is in the third position of the well-ordered set. The notions of ordinals and cardinals can help us to understand why some people prefer to start the naturals with 1 and why some people prefer to start with 0. If we're talking about cardinal numbers, it's useful to start with 0 since we often want to talk about having no apples or $0 in my bank account. If we're talking about ordinals, it's useful to start with 1 since then the ordinal number corresponding to the first number in the naturals will be 1. If I write out like this, it's 1, 2, 3, so on. So the ordinal number of this, of the 1 would be 1, the ordinal number of the 2 would be 2, the ordinal number of the 3 would be 3, and you don't have that if you start with 0. But, do whatever you want. But one interesting point to make is that any well-ordered set will be isomorphic to the natural numbers, meaning that if we have a well-ordered set S, we can construct a one-to-one mapping from S onto the set of natural numbers. So in symbolic terms, we could say if we have a number I in the set of naturals like that, there exists an SI. So this is the SI would be from S and the ith place. So like if I was 2, it would be this guy right here, or like that. So I and N, there exists an SI which maps to the number I for all I in S. Boom. So in order to go about constructing the set of natural numbers, we can use my good friend Giuseppe Piano's arithmetic, which is based on 3 primitive ideas. And those ideas being 0, number, and successor. I think that's how you spell that word. By successor, he means the next number in the natural order. So if our number was 1, the successor would be 2, 2. If it was 2, it would be 3, like that. And by number, he means, in this case, an element from the class of natural numbers. But just remember that these axioms can be stated much more generally on any well-ordered set where 0 is defined as the least element in the set. So the 5 primitive axioms are as follows. 1. 0 is a number. 2. The successor of any number is a number. Okay. 3. No two numbers have the same successor. And 4. 0 is not, this symbol means not, the successor of any number. And 5, let's see, oh, this is a long one. Any proper, beautiful sparrow. Any property which belongs to 0 and also the successor of any number which has the property belongs to all numbers. That is a long one. So the last of these, number 5, defines what is known as induction, which is a little bit complicated, but I'll give a short definition. Basically, it defines hereditary properties in sets. We define the natural numbers as the posterity of 0 with respect to the relation of a number to its immediate successor. So if we call this relation n, any number m with the relation n to m plus 1 would have this property, basically. So the property would be called hereditary with respect to m, or simply n hereditary, whenever the property which belongs to a number m also belongs to m plus 1, i.e. to the number m which has the relation n. Now I'm quoting from Russell here because I think he does a good job of explaining the problems with extending mathematical induction to infinite quantities, which is extremely important in recognizing the useful qualities of the axiom of choice. Quote, mathematical induction affords, more than anything else, the essential characteristic by which the finite is distinguished from the infinite. The principle of mathematical induction may be stated popularly in some such form as, what can be inferred from next to next can be inferred from first to last. This is true when the number of intermediate steps between first and last is finite, but not otherwise. Anyone who has ever, turn the page, watched a goods train begin to move will have noticed how the impulse is communicated with a jerk from each truck to the next, until at last even the hindmost truck is in motion. When the train is very long, it is a very long time before the last truck moves. If the train were infinitely long, there would be an infinite succession of jerks, and the time would never come when the whole train would be in motion. Nevertheless, if there were a series of trucks no longer than the series of inductive numbers, every truck would begin to move sooner or later, if the engine persevered, though there would always be other trucks further back which had not yet begun to move. When we come to infinite numbers, where arguments from mathematical induction will no longer be valid, by contrast, the almost unconscious use that is made of mathematical induction where finite numbers are concerned will become clear. Now, there is just one more topic to cover in our climb up the ladder to the axiom of choice, and that is the concept of infinite numbers. The problem that infinite numbers pose is an ancient one that hasn't been solved until recently by Georg Cantor in the 19th century. So our present task is to find the cardinality of the natural numbers. That is, find the number of terms in the set of natural numbers. It's clear that the cardinality of the naturals cannot be a number itself, because if n is a natural number, then the number of terms from 0 to n is n plus 1. Therefore, the total number of naturals must be greater than n, whatever your choice of n may be. Thus, the number of naturals must be a new number different from all the rest, not possessing all its inductive properties. That is to say, if 0 has a certain property and n plus 1 both have that same property, then our new number need not possess it. And now I'm quoting again here. The most noteworthy and astonishing difference between an inductive number and this new number is that this new number is unchanged by adding 1 or subtracting 1 or doubling or halving or any of a number of other operations which we can think of as necessarily making a number larger or smaller. The fact of being not altered by addition of 1 is used by Cantor for the definition of what he calls transfinite cardinal numbers. Now, we can introduce the star of this section, and his name is Aleph Null, as in the first letter of the Hebrew alphabet, followed by a 0, as in null. Aleph Null is a transfinite number, and it is the number of terms in the set of natural numbers, and subsequently the number of terms in any progression as defined by Peano's axioms. Because remember, while there is a first term in any progression, there is no last term. So a set has cardinality Aleph Null if and only if it is countably infinite. That is, there is a bijection or one-to-one correspondence between it and the natural numbers. Now you might be thinking to yourself, how can something be both countable and infinite at the same time? And what does countable even mean? Well, a better word for countable might be listable. This list is allowed to be infinitely long, but any spot on the list must be given a finite ordinal number, first, second, third, and so on. Countability is an important distinction to make because we are about to talk about some sets that are not countable, in particular, the set of all real numbers. But first, a little tangent. If you're wondering how you might actually go about writing out this whole list, it's pretty easy and it'll only take a minute, literally. So if we have our watch, that's a watch, and we got, like that. Then here's how we're going to write out all the naturals in 1 minute. So first, take 30 seconds to write 0. Then we're going to take 15 seconds to write the number 1. Then we're going to take 7.5 seconds to write the number 2. And then we're going to take 3.715 seconds to write the number 3. And then we're going to take, right here, 1.875 seconds to write the number 4. And we're just going to keep doing this, taking half the amount of time every time we write a number to write out the next number. And then by the time 1 minute is up, provided you have an infinitely large chalkboard, you will have finished writing all of the natural numbers in just 1 minute. Easy. I suggest you all go and try this at home. It's a pretty fun exercise. So let's quickly finish up with our, how do you even write this letter? That's not how it is. It's got like some weird curves to it. Like this, like that. I don't know. That's our Aleph Null. You can look up how it looks, or maybe I'll throw a picture on the screen because I do not know how to write that letter. But anyway, what are some other sets of numbers with Aleph Null terms? Well, first, let's recall the form of the series of natural numbers. So we have 1, 2, 3, dot, 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 n, dot, 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 like that. And remember that any series which we can make into a progression using those 5 axioms we talked about also has Aleph Null terms. So let's see. So for example, we have the series of even numbers 2, 4, 6, dot, 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 2n, dot, 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 the cardinality of this set is also, guess, is it 1/2 Aleph null? No, it's just Aleph null because it's just a progression. So this fact can appear quite paradoxical at first glance, and I'll show you two more seemingly paradoxical results. So the first is that the number of whole numbers, positive or negative, has the same number of terms as just the positive integers. And to show this, I can arrange the whole numbers into this series: 0, -1, 1, -2, +2, and so on, -n, comma, +n, like that. And so the cardinality of this set is once again Aleph null because it's just another progression. The second result is that we can prove that the number of fractions or rational numbers, which if I remember right, I think is denoted Q, like a double stroke Q, like that. I'm pretty sure, or maybe it's a Z. I'm pretty sure it's a Q though. The cardinality of that set is also the same as the number of naturals. So this is a series which is a little confusing, so I'm going to skip over a few of the details, but feel free to pause and write down some numbers to make sure that I'm not lying to you, because I would never, ever lie to you. So the first step is to define Stern's diatomic series, which goes like this. A1 equals 1, A2k equals AK, and A2k plus 1 equals A sub k plus A sub k plus 1. So then we're going to use this in the form of A sub n over A sub n plus 1 to write out all of the rational numbers in a progression. So here's what it'll look like. 1 over 1, comma, 1 over 2, comma, 2 over 1, 1 over 3, 3 over 2, 2 over 3, 3 over 1, yeah, so on, a n over a n plus 1, like that. So you can use this series to write out all of the rational numbers, and it proves that, once again, the cardinality of this set is Aleph null. And if you want an alternate description, you can find one in Russell, which I think is even more confusing, where he says, if the sum of numerator and denominator in one is less than in the other, put the one before the other. If the sum is equal in the two, put first the one with the smaller numerator. So if you can decipher that cryptic language, then nice. You can go at the front of the set of our well-ordered smileys, like that. You can be this guy. That'd be so sick, wouldn't it? Oh, look at this guy. I think he's getting a nut. Do you see this guy? I think he's getting a nut. Oh. Wait. Is he getting a nut? Oh, shit. I think he got a nut. This is important, guys. Listen up. As implied earlier, it is not the case that all infinite collections have Aleph null terms. For example, the cardinality of the real numbers is greater than the cardinality of the natural numbers. This is really important. If you don't know what a real number is, then let me say first of all that it's a little bit misleading for them to be called real numbers. Real as in like that, because they're not, real. Like if I told you to go find me a number 3, then you can't find a 3. You can find a representation of a 3 that looks like this, but you can't find a 3. You can find threes, a trio of objects, but you can't find a 3. I don't know. That might be a little too philosophical, though, for the philosophy hour. Anyway, uh, a real number is not any more real than any other number, but basically, it's a quantity that can be expressed as an infinite decimal expansion. So here's a few examples. We have 1.00000000000 dot dot dot, or we have 2.0000000. So yeah, like that. Or we could have like 0.5000000, more commonly known as 1/2. Or we could have, here's a pretty famous one, 3.14159 something 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 equal to everybody's favorite ratio, pi. Or we could have even something like 2.182881828. I think that's how it goes. It's something like that. Dot 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 equals E. Everybody loves the letter E, the most common letter in the English alphabet. And also the favorite number of everybody's favorite mathematician, Euler, the goat. Anyway, the real numbers are interesting in the fact that they are continuous, or to use another term, they are dense. This means that for any two real numbers, no matter how close together they are, we can find a third number between the two using the arithmetic mean, also known as adding the two numbers and dividing them by 2. So in symbols, we can say like this: A, comma, B, oops, not comma, in R, okay, starting off strong. For all A is less than B, okay, there exists a C equals A plus B divided by 2. Here's our arithmetic mean we were talking about in R, okay, such that A is less than C is less than B. Boom. So this is just saying that for any A and B in the real numbers, we can find a C that is greater than A but less than B. So in between. So that begs the question, what is the cardinality of the reals? We were talking about that over there because we know it's greater than the cardinality of the naturals, but what is it? Before we can talk about that, though, we need to talk about a little thing called, that's an O, power sets. Power sets. They sound powerful, and they are actually, surprisingly, pretty powerful. So the power set of a set is the set of all subsets of the set, including the empty set and the set itself. So let's give a little example. So here's our set. S equals X, Y, Y, Z. Okay, there's our cool set. So the power set of S, which is denoted with like a fancy P that I can't really draw that well. The power set of S is equal to this set. There's the null set, which is denoted by a 0 with a line through it, which is just an empty set, like there's nothing in it. Then there's the set X. There's the set Y. Oops. There's the set Z. Then we're getting a little wild here. There's the set XY. There's the set YZ. And finally, there's the set, my curly braces are getting a little crazy, the set XYZ. So it's just the set of all the subsets of the set, including the empty set and the set itself. Empty set, set itself. And let's talk about the size of the power set of the set. So The cardinality of S is 3. There's 3 terms in the set. And the cardinality of the power set of S is 1, 2, 3, 4, 5, 6, 7. X, Y. Oh, X, Z. 8. There's 8 terms. And the reason why it's 8 terms is actually very important. So, it's time to introduce our very first choice function, the titular choice function of the axiom of choice. So, the choice here is X in the power set or not in the power set, or the subset of the power set. So for example, if this is our subset Y, is X in or not in? Well, it's not in because it's just Y. So there's 2 choices for each term, for each subset. It can be in or not in. So 2 choices times 3 terms is 2 times 2 times 2 equals 8. And we already determined that the cardinality of our power set is 8. 8? That looks like an 8. So what gives? Well, I just said what gives, but you can also represent this as 2 to the 3, which is very important. So basically, the cardinality of any power set expressed as like this is 2 to the cardinality of the set itself. Morning dove on the sidewalk, walking around. Morning dove. Whoa. Gonna go ahead and erase my last take here because this take is gonna be the one. I can feel it. So this brings us back to the question at hand, which is, what is the cardinality of the reals? So the real numbers, also known as the continuum, the cardinality is this blocky C shape, but I'm probably just going to write it as a normal C because it's cooler, I think, because curves and stuff. So the C is equal to the cardinality of the power set of the natural numbers. So you can write it like this, is equal to the power set of the natural numbers, which means it's equal to 2 to the aleph null. Remember that little squiggle that I don't know how to draw is aleph null. So to get an idea as to why this is true, think about the fact that any real number can be expressed as an infinite decimal. So you can think of an infinite decimal as a series of the terms of a power set in which you can put in any order you want. Then you can think of the null class as the terminating digit in the decimal. So if we had like a number 3.14159 terminate, because we're saying, no, you're not irrational, you're actually rational now, pi. What are you going to do about it? This terminating decimal, you can think of it as the null class. And I don't know if any of this is actually true. I'm kind of just making it up, but it seems true in my head. So we're going to go with it. But then how do we know that 2 to the aleph null is greater than aleph null itself? Since, we know that aleph null equals, for example, aleph null times aleph null equals aleph null squared equals, I don't know, like 2 aleph null equals, whatever. You can keep going all day. Equals 2 aleph null plus 1 divided by 5 factorial. That's crazy, but it's true. It's crazy, isn't it? So why should 2 to the aleph null be any different? So to show this, we're going to use a famous argument called Cantor's diagonalization proof. And we're going to do this in binary, but it can be also explained in whatever base you want with a little bit of work. But I think binary is kind of the easiest. So a convenient fact of the reals is that the cardinality of the reals on the open interval, negative infinity to infinity, is equal to the cardinality on the closed interval, the unit interval, 0, 1. And if you don't understand this, like, think about it for a moment and put your answer in the comments below. But anyway, so we're going to construct a mapping of every natural number to a unique binary float value. So let's do that. So first natural number, 1. It's up there with one of the best natural numbers in my opinion. So this is going to map to, let's make up a float, 0.11111111111 dot dot dot. All right, 2 will map to 0. Let's say 0.000000000. Okay. And maybe 3 will map to 0.10101011010 dot dot dot. All right, and then maybe our maybe 4 maps to like 0.0101010101, something like that. All right. So this goes on for infinity this way, and this all goes on for infinity this way. So we have infinite strings and an infinite number of natural numbers. So now we're going to take a diagonal sampling of every string in the list to construct a new binary string, which we're going to call alpha. Alpha, like that. Like I'm the alpha dog, the alpha male, and also the alpha wolf, all 3 at once. So we're going to take the first value of the first string, this guy, the second value of the second string, this guy, third value of the third string, this guy, fourth value of the fourth string, this guy, and we're going to put that in our string right here, our new string. But here's the catch. For every value we sample, we're going to take the complement, or also known as a 0 is a 1 and a 1 is a 0. So 1 turns into 0, 0 turns into 1, 1 turns into 0, 1 turns into 0, and so on. So what we have just done is created a brand new string that does not exist anywhere in our list of previous strings. And this is important because we showed that if you match up every single natural number, remember we had every single natural number here, to a unique string, every one of these strings has to be different, we can get a completely new string that does not appear anywhere in the natural numbers. And the reason why we know it does not appear is because, let's say this string is somewhere in here, then we know that by definition, the nth digit of this string will necessarily be flipped. So every single string that could exist in our mapping sort of thing will differ by at least 1 digit. And that means that the cardinality of the reals must absolutely be greater than the cardinality of the naturals. You see that? Male northern cardinal singing his song. He is attracting his mate so that he can do nasty things. All right, so here's a proof of the more general thing we were talking about, that the power set of A must be strictly greater than the set itself. So this is called Cantor's theorem. See if you can understand what is going on, because I cannot. So let F be a map from A to the power set of A. Then F is defined as A to power set of A is not surjective. As a consequence, the cardinality of A is strictly less than the power set, or the cardinality of the power set of A, holds for all A. And here's the proof. Let's see. Consider the set B is x in A such that x is not an element of f of x. Suppose to the contrary that f is surjective. Then there exists an x in A defined such that f of x is in B. But by construction, x is only in B if and only if x is not an element of f of x equals B. This is a contradiction. Thus, f cannot be surjective. On the other hand, G is defined such that A is a map to P of A, is defined by X is a map to the set with element X is an injective map. Consequently, the cardinality of A is less than the cardinality of the power set of A, Q, E. What are you doing here in this? What are you doing in this hole? Well, while I got you here, I might as well tell you about these freaking numbers. So, the final thing to consider concerning infinite cardinal numbers is like we got aleph 1 and maybe aleph 2, and then, well, we might as well talk about like aleph 3 as well, and then maybe aleph 4 and I don't know, aleph 5 too. But the series of higher order aleph numbers isn't really too complicated once you get a firm grasp of aleph null. Now that we understand that it's trivially easy to create sets that are strictly larger than other sets through, for example, power sets and that sort of thing, as proved by Cantor's theorem, then let's see, that's like all cool and all, but we still need to create a classification system for these higher order infinities. And mathematicians do this through a little trick that I like to call, you say, I define this thing to exist, and then it exists. It's a really nice trick, actually. So then we're going to define aleph 1 as the set of the smallest infinite set larger than aleph null, and then consequently it's also the smallest possible set of uncountably infinite objects. Similarly, aleph 2 is the smallest infinite set larger than aleph 1, and so on to infinity. But now, dear viewer, poor viewer who is stuck in a hole, if you have a brain, you should be shouting at your screen. But where does 2 to the aleph null and the cardinality of the reals fall on the aleph scale? So if you're shouting this question, which I know you are, go ahead and shout it into the comments section. And while you're there in the comments section, like maybe smash that subscribe button and hit the like button too, and ding that notification bell, of course. And you know, that sort of thing. Or maybe like send me like a Amazon gift card or like a scholarship or something like that. But you know, like smash that like button to lock in your vote. So if your brain is really big, you will have put in the comments section, I don't know, to that question, because it is actually an impossible question to answer, as outlined by Kurt Gödel and Paul Cohen, who proved this. They proved that using the standard axioms of set theory as outlined by Zermelo and Frankel, even with the axiom of choice, which we haven't talked about yet, this question is independent of ZFC set theory, which is Zermelo-Frankel axiom of choice. C stands for choice. So the continuum hypothesis, which is like this hypothesis that we're talking about right now, actually, it was first stated by Cantor himself in the 1870s, predicting that 2 to the aleph null was equal to aleph 1, the smallest set of uncountably infinite stuff. And this was a very unsolved question for a very long time until our good friends Gödel and Cohen came along in the 40s and 60s, respectively, to like prove some stuff. And they showed that both the continuum hypothesis and its negation, the not continuum hypothesis, are both true, meaning that this question is independent of ZFC set theory. So without some additional axioms, which we don't have, it is actually a meaningless question to ask. So don't even ask it and delete that comment below. Please and thank you. Hey, John Howell. What
What's
do you
up?
think about the axiom of choice?
Well, first off, I want to thank Cole Kleinens for letting me on his philosophy hour video. Um, really, I just think that the axiom of choice is really freaking sick. Like, it's just such a cool concept. Like if like doing bicep curls and bench pressing was like a mathematical theory, then it would be the axiom of choice.
That is fast.
Thanks, Cole.
All right, thanks, John.
No. Actually, is it in philosophy?
Sort of.
You're talking about the philosophical axiom of choice?
So, now that we have covered the basics of infinite cardinal numbers, we can switch gears and talk about everybody's favorite thing, infinite ordinal numbers. Who doesn't love infinite ordinal numbers? I'll make this section a little bit faster because my love for transfinite numbers only extends so far, which is to say it extends aleph null phi. I love transfinite numbers, so this section is going to be very long as well, but not as long as the last one still. So let's return to the series of natural numbers. As you will recall, 0, 1, 2, 3, dot, 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 and dot, 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 like that. Who doesn't love the series of natural numbers? So, if we are going to treat this as any normal progression and assign an ordinal to each number depending on its place in the sequence, what would be the ordinal associated with the last number after the dot, dot, dot? What would it be? It would be, get ready, get ready, get ready, omega. Now that's a good Greek letter right there. So this will give us our first countably infinite ordinal number. So basically, omega is to ordinals what aleph null is to cardinals. And if we had a progression such that the last number was in omega-th place, the series would have aleph null terms. But the ordinal's nature of being explicitly tied to progressions has some strange consequences. And I will illustrate this with a little example. So we're on a little playground here. This is a slide. It's a math playground, so the slide is an asymptote and continually approaches the ground but never actually touches the ground. And there's that sort of thing at a math playground because this is a math video. And we have two little children, two little kindergartners at the math playground, and they're just hanging out. This one's got some spiky hair, and this one's got like he's bald because he has a terrible illness, sadly. This is child number 1, this is child number 2, and here is a conversation between them. So they, being two little children, are arguing about who can name the largest number. So child number 1, he says, that's speaking here. He says infinity. Okay, that's a good try. But then child number 2, he's going to respond. He's going to respond and he's going to say, infinity is not a well-defined term and cannot be treated as a number. And you should limit the scope of our discussion to cardinal numbers as to avoid paradoxical arguments, Mr. Child number 1. And child number 1, thankfully, realizes the error of his ways, but still responds quite foolishly with this answer. He's going to say, aleph null. Okay. But then, that's a good try, but you can always go with like aleph 1 or aleph 2 or Aleph 3 or, like Aleph 4 or, something like that. Maybe like Aleph 5. But child number 2 is also kind of dumb. So he's going to say this. He's going to say Aleph null plus 1. See, child number 2 thinks he's got child number 1 on the ropes here. But then obviously child number 1 says Aleph null plus 2. Then 2 responds with 3, then 1 responds with 4, and they keep going like that. And the argument ceases to be interesting. But little do both of them know that Aleph null actually equals Aleph null plus 1, also equals Aleph null plus 2, also equals Aleph null plus 3, and so on. So while they think they're each saying bigger numbers than each other, they're actually both saying the exact same number. But if we were to repeat this entire conversation again, but instead of deciding to talk about cardinal numbers, they were to decide to talk about ordinal numbers, this is where it gets interesting. So child number 1 says omega. Child number 2 says omega plus 1. And in this case, child number 2 is not making a bad argument here, because in reality, omega is less than omega plus 1. How in the world is that even possible? Wow, guys, look at this beautiful buzzing bee. Spring has truly sprung here at the university campus. So to understand this, let's talk about 2 seemingly similar progressions. The first one is K 0, 1, 2, 3, N, like that. All right, and the second one is going to be just 0, 1, 2, 3, N, K. So in the first case, K comes, it's the least element in our well-ordered set. And in the second case, after we've expended every single natural number, we're going to write K at the very end. So the ordinal number associated with the first set would be omega, of course, because it's just our normal progression. But the ordinal number associated with the second set is going to be different. It's omega plus 1. So how is that even possible, since, Aleph null plus 1 is just Aleph null? Well, it's because this thing is coming at the end. So in this case, the K just becomes our new least element. We could also put K in the middle of our progression and it would act the same way. And that's because every ordinal number is just going to shift over 1. So in this set, where 0 has ordinal 1, 1 has ordinal 2, 2 has ordinal 3, in this case, K has ordinal 1, 0 has ordinal 2, 1 has ordinal 3, and so on. So everything just shifts left 1, and there's no real troubles. But in this case, we're expending all of our ordinal numbers. Our last term is going to be ordinal omega, so then that leaves nothing left for our K here, which necessarily must become omega plus 1. So this means that ordinal numbers are not associative. So 1 plus omega equals omega does not equal omega plus 1. Very interesting. So here's another series you could make. We could go 1, 3, 5, 2 to the n plus 1, 2, 4, 6, 2n, like that. So we have all of the odd numbers, and then once every single odd number is expended, we're going to restart the progression, where we're going to put all of the even numbers instead. And can you guess what the ordinality of this set would be? It would actually be 2 omega because we have two progressions in a row, so there's 2 omega, terms. Or, well, no, that's not true. It still has aleph null terms because it's a progression, but uh, the last element, if we had an element, say like C, last. Well, if we had an element C at the end, then it would be 2 omega plus 1, but you get the idea. So this series would have ordinality 2 omega, and you can continue this way, creating, omega omega if you had omega series of omega terms or omega ordinality, whatever. You can do whatever you want basically and get however large or weird or wacky of a number you can possibly set your mind to. But then there's also higher order omegas to consider. The smallest ordinal corresponding to an uncountably infinite set is omega 1, just like we have an aleph 1. So a set where the last term is in omega 1th place would have aleph 1 terms. And there's same if we replace this with a 2. The last set is in omega 2th or the last element is in omega 2th place, corresponds to a total cardinality of aleph 2. And things can get even wilder than that. For example, we have aleph omega, so that's, I don't even know what that would mean. Like it's a set with aleph null terms, but or it's the omega smallest set of aleph null. I don't know. It's weird. It gets really weird, but we can't really talk about that because one, I don't understand what that means, as you can see, and two, we still have to talk about the axiom of choice. Let's. Oh, what's up? Didn't expect to see you here. One moment. Uh, okay, what's going on? So, now I think we have more than enough background to fully understand the axiom of choice, that is. The axiom, at first glance, sounds fairly inconspicuous, but it contains far-reaching consequences on the foundations of many fields. But first, wait for it, what is an axiom, and what is a choice? Well, first, what is an axiom? It's basically a shared set of assumptions that outline the rules of a given structure. They are carefully enumerated so that any two people working on the same problem in the same field know the shared set of assumptions and rules that they're working under. And a choice function is a little bit harder to explain in words alone, but essentially it's a function that chooses one element out of each non-empty subset of a set A, which would be called a choice function for A. There are a few different ways to write out the definition logically, but the most common way is like this. Let beta be a set. So a collection indexed by beta is a collection of sets S sub I with sub I in beta, like that. So in other words, the collection contains one set for each element of beta. So this can be expressed as a choice function like this. So our choice function f is defined such that beta is a mapping to the union of I in beta. That's supposed to be a beta, not a heart. To I guess it'd be 2 omega of S sub I such that f of I is in Si for all I in beta. So this seems really complicated, but in reality, it's not actually that bad. So let's look at a simple example. Let H be the collection of non-empty sets of 0, 1, and 0, 1. So i.e. H looks like this. 0, 0, 1, damn. Okay. 0, 1. 0, 1. Like that. Okay? So then H has the two distinct choice functions, f1 and f2, given by my curly braces are getting a little unfortunate, but that's the price you have to pay to make an extra long Cole Kleinitz Philosophy Hour special for all the lovers and fans of Cole Kleinitz all around the globe. 0, 1, 1. So look at the difference here. So when there's no choice to be made, such as in these two examples, both choice functions choose the same thing because there's only one choice. But when there's a choice to be made to output a singular value, either 0 or 1, the choice function 1 chooses 0, choice function 2 chooses 1. And that's pretty much all there is to it. A more interesting example could be like a choice function provided by taking H to be the set of unordered pairs of real numbers, and the function that the choice function would be the thing that assigns each pair its least element. And then you could have another choice function that does the opposite thing. It assigns each pair what the maximum element is. So it doesn't really have to be that complicated. And now we can finally get to the axiom of choice. So here are two equivalent definitions to start us off. First one, any collection of non-empty sets has a choice function. Or equivalently, any index collection of sets has a choice function. I think these are both, fairly straightforward and almost self-evident. Here's a more formal definition. So let me erase this. This one's going to take a little bit of room. So, for any relation R between sets A and B, for all x in A, there exists a y in B with the relation R with the domain x comma y. Okay, so if this is true, then there exists a function f, a choice function f, defined such that A is a map to B, and how do you write this symbol? It's it's like this. And are you impressed that I got that? And for all x in A with the relation R with the domain x, fx. Boom. Boom. Does that make sense? I think that makes sense. So in other words, every relation contains a function having the same domain. Think about it. Mr. Robin.
Hi, Julie.
I'm coming for you. I'm coming for you. Where are you going, Mr. Robin? So, a more intuitive definition of the axiom of choice might make use of something called the Cartesian product, which is actually the logical basis for multiplication. So, for example, if we have a set alpha equals x, y, z, then what is alpha cross alpha? So let's go through it. So we have x comma x, x comma y, x comma z, and then we have y comma x, y comma y, y comma z, and then we have, let's see here, z comma x, z comma y, and z comma z. So this might become more familiar when I point out that the cardinality of A is 3, 1, 2, 3 terms, and the cardinality of A cross A is, let's see, if this is a set like this, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what this is really saying, sort of, is that 3 times 3 equals 9. So that's why it's the logical basis of multiplication. So if we have a series of terms multiplied together and the product of the series is 0, then we know that at least one of the terms must be 0. Likewise, if we take the product of a series of sets and the answer is the null class, which remember is just the empty set, there's nothing inside it, then and also the null class has cardinality 0, then we know that at least one of the factors must also be the null class. So this is more or less evident when we have a finite number of terms because we can use our good old friend induction. But as discussed earlier, induction as a means of proof completely breaks down with an infinite number of terms. But thankfully, using the axiom of choice, we can prove the infinite version of this statement, which basically reads, the product of a series of sets is only null when it has at least one null factor. And written logically, it would look like this. So S sub I does not equal the null class for all I in beta. So if this is true, then let's see here, we have the product, the big pi just means like a product series sort of thing, I in beta to omega of S sub I does not equal the null class. Yeah, I think that's more or less evident. So here's some equivalent statements of the axiom of choice for a variety of different people. For all the linear algebra freaks out there, we have every vector space has a basis. For all the people who love to put things in order, we have every set can be well ordered. For all the discrete math lovers, every connected graph has a spanning tree. For people who enjoy misleading statements that appear self-evident until extended to infinite sets because induction does not apply to infinite sets, we have, if two sets are given, then they must either have the same cardinality or one has a smaller cardinality than the other. Let's see. For the types of people who love dropping big words in conversation to make them seem smart, there are plenty of examples. Such as, every unital ring other than the trivial ring contains a maximal ideal. Or, for example, the closed unit ball, wait a minute, the closed unit ball of of a normed vector space over the reals has an extreme point. Yeah, you can eat chips. All right, King B. What do you think about the axiom of choice?
Oh, the axiom of choice. In the Creative Act by one of my favorite music producers, Rick Rubin, he says, "I'm strongly affected by the sun. When it's a bright day, I feel energized. When it's gloomy, I'm gloomy. On those overcast days, it helps to tune to the fact that the sun is still there. It's just hidden behind a thick layer of clouds. At noon, the sun is high in the sky, regardless of how light or dark it is outside. In the same way, regardless of how much we're paying attention, the information we seek is out there. If we're aware, we get to tune into more of it. If we're less aware, we miss it."
Damn, that's powerful, King
Yeah.
B. That speaks to my understanding of the axiom of choice as well.
What's your understanding of the axiom of choice?
It's like what you said, right, Reese?
Facts.
Facts. Okay, thanks, King B.
Yeah, of course. Cool.
All right, bye.
Is that what?
All right, let's see here. Yikes. So, like the question of where 2 to the aleph null falls on the aleph scale, the truth and consistency of the axiom of choice was a huge debate in the early 20th century especially, but still continues today to a certain extent. Zermelo introduced the axiom to the world in 1904 as a part of his influential system of set theory. His original purpose was to establish a central principle of Cantor's set theory, namely that every set admits a well-ordering and so can be assigned a cardinal number. Zermelo's 1904 introduction of the axiom, as well as the use to which he put it, provoked considerable criticism from the mathematicians of the day. The main objection raised was to what some saw as its highly non-constructive, even idealist character. While the axiom asserts the possibility of making a number of even an uncountable number of arbitrary choices, it gives no indication whatsoever of how these choices are actually to be defined. This was particularly objectionable to the mathematicians of a constructive bent, such as the French empiricists Baer, Borel, and Lebesgue, for whom a mathematical object could be asserted to exist only if it can be defined in such a way as to characterize it uniquely. Zermelo's response to his critics came in the form of 2 papers in 1904. In the first of these, he reformulated the axiom in terms of transversals. In the second, he made explicit the further assumptions needed to carry through his proof of the well-ordering theorem, which states that every set can be well-ordered. These assumptions were groundbreaking as they constituted the first explicit presentation of an axiom system for set theory, which obviously today is extremely important. As the debate concerning the axiom of choice continued, it became apparent that the proofs of a number of significant theorems made essential use of it, thereby leading many mathematicians to treat it as an indispensable tool. Hilbert, for example, came to regard the axiom as an essential principle of mathematics and employed it in his defense of classical mathematical reasoning against the attacks of the intuitionists. Although the usefulness of the axiom quickly became clear, doubts about its soundness remained. These doubts were reinforced by the fact that it had certain strikingly counterintuitive consequences. The most interesting of these was Banach and Tarski's paradoxical decompositions of the sphere, which states that any solid sphere can be split into finitely many pieces, which can then be reassembled to form 2 solid spheres of the same size. And any solid sphere can be split into finitely many pieces in such a way as to enable them to be reassembled to form a solid sphere of arbitrary size. The reassembly process involves only moving the pieces around and rotating them without changing their shape. However, the pieces themselves are not solids in the usual sense, but infinite scatterings of points. The theorem is called a paradox because it contradicts basic geometric intuition. doubling the ball by dividing it into parts and moving them around by rotations and translations without any stretching, bending, or adding new points seems to be impossible, since these operations should intuitively preserve the volume. However, this intuition is not applicable here because in this case it is impossible to define the volumes of the subsets of the ball. But ultimately, just like 2 to the aleph null, the question of the consistency and independence of the axiom of choice was put to rest by our good friends. I just got busted in on by this lady. Anyway, let's let's continue. Anyway, as I was saying, the consistency and independence of the axiom of choice was put to rest by our good friends Kurt Gödel and Paul Cohen. In 1938, Gödel proved that the axiom was indeed consistent with the other axioms of set theory, which was a huge blow to constructionists all around the globe. Then, in 1963, Paul Cohen proved the independence of the axiom from the other standard axioms of set theory. This means that it can neither be proven nor disproven using the other axioms, so its truth is ultimately dependent on personal preference and convenience. Most mathematicians today accept the axiom as it makes certain results much easier or even possible where they would otherwise not be. The axiom of choice, though, seems starkly out of place in modern mathematics, analogous to Euclid's fifth postulate, which upheld the foundations of geometric thought for 2,000 years until it all came crashing down with the advent of hyperbolic and other non-Euclidean spaces. The axiom defies standard intuition, yet supports entire fields of set theory, analysis, and more. It stands as a testament to the layers of abstraction inherent in purely logical math, which at first glance obscures all meaning, but in reality opens the door to a new realm of possibilities. Thank you for watching.